Welcome to the ENME 351 video lecture series. This is part one of a two-part installment on actuation. This lesson takes an introductory look at actuation. What is an actuator? Well, an actuator is a transducer converting to mechanical energy. So for example, I may have some electrical energy and I want to convert that to a force output, let's say, right? So I would use an actuator to accomplish that task. We can think of an actuator effectively as the reverse of a sensor. In the case of an actuator, we are acting on an environment that's providing a load to our actuator. Thus, the actuator is the direct interface to the environment. To drive the actuator, I'm ultimately going to require some sort of power amplification and modulation. So I can effectively think of these as my interface electronics between my actuator and something like my microcontroller. My actuator at this point, it's providing a physical signal. That might be a torque or a displacement, for example. In this case, I typically have something like a voltage, but let's say it's a pneumatic actuator. I might have here some fluid flow pressure. And then between my microcontroller and my interface electronics, that's typically a voltage. One interesting aspect of actuators is I can sort of draw a dividing line here. And on one side is going to be my low power side. So on this low power side, it might be like a 3.3 or a 5 volt signal and typically very low current. On the other side, however, it's typically a fairly high power output. So for example, it might be amps of current compared to milliamps coming out of an Arduino. As a quick example of this actuator pathway, let's take a look at an electromagnetic actuator. Here we have a basic DC motor with an output shaft. So here's my motor, here's my shaft. There may be some load applied to that output shaft, so it's providing some output torque, as well as some rotational velocity, omega. And so these are really the two outputs of my motor, the torque and the speed. We can represent this motor with a fairly simple circuit. We have a resistor, an inductor, and a voltage supply all in series. I'll connect to my motor my interface electronics, so my power amplification and modulation electronics. And the way I'll do that is typically through the implementation of transistors. Transistors are going to permit me the opportunity to implement a separate power supply. So now I have a separate power supply here that I'm calling V motor. And then this output from my transistor that'll be connected to my motor to drive the motor. On the left side of my transistor, I'll have my control inputs coming from something like my Arduino. For example, we could use a digital output pin on our Arduino to provide that control signal input to the transistor. So here's the basic layout for an electromagnetic actuator. And once again, we could sort of draw a line down the middle. And on the left would be our low power side of things. And then on the right would be our high power side of things. Another example of a common actuator would be a pneumatic actuator. In this actuator, I effectively have a piston with a valve here that I could fill, say with some fluid flow to increase the pressure here and move this piston back. And then maybe there's a spring or something to act as sort of restoring force. But my primary outputs here are going to be some force and displacement. In this setup, my power amplification and modulation electronics would ultimately be driving this valve. Now, since it's a pneumatic system, I'm going to have some reservoir of compressed air or some other compressed fluid, which I'll actually be able to send into this piston here by actuating this valve. So this compressor then, this is sort of the fluid equivalent, the pneumatic equivalent of the power supply from the preceding slide with the electromagnetic actuator. And then ultimately we'd have something like an Arduino providing this control signal, which is ultimately responsible for actuating the valve. So maybe it's a solenoid or something like that. There are a number of metrics that we need to evaluate when choosing an actuator for a particular application. First one we want to keep in mind is the torque or the force that can be provided by the actuator. Another way to think about that would be what sort of loads I could actually apply on my environment. Another metric would be speed, so effectively how fast can I move, how fast can I actuate. And this is effectively the bandwidth. Output power, that's going to be the combination of the speed and the torque outputs. One common metric for output power is the specific power, which is defined in terms of the power that can be provided per kilogram of the actuator. So if I have an application that requires a lot of power in a small package, the specific power is a metric that I'm going to be interested in. Efficiency, that'll be defined in terms of output power divided by input power, where for a mechanical actuator, we're looking at something like force times a distance. A mechanical output will be the output power divided by an input power, which is almost always an electrical input power in terms of watts. And then depending on your particular application, there's obviously going to be other metrics that you're going to be interested in. I've put some here. The step size, right? It's going to be, what is the minimum step in which I can increment my actuator? If I have a real interest in controlling position quite accurately, maybe for the printing head of a 3D printer or for a tip tilt mirror for an optical alignment, then the position accuracy of my actuator is going to be of importance in that scenario. And so there are a whole host of metrics of interest with regards to actuators that are of more or less importance depending on your application.